A heap is a specialized tree-based data structure that satisfies the heap property. In a heap, for any given node, the value of the node is always ordered with respect to its parent. This ordering can be one of two types. The first one is max heap. In a max heap, for every node except the root, the value of a node is at most the value of its parent. This means that the largest element is at the root and elements get smaller as you traverse down the tree. So all the nodes on the left should be smaller than that node's value, and all the nodes in the right should be less than that node's value. Meaning it is sorted in a way that all the child nodes must be smaller than the current node. And in case of min heap, it is the opposite. For every node except the root, the value of a node is at least the value of its parent. This means that the smallest element is always at the root, and elements get larger as you traverse down the tree. And the heap is also a complete binary tree, which means that all levels of a tree are fully filled, and if the last level is not complete, the nodes are filled from left to right. Priority queues are often implemented using a binary heap, although it's not the only way to implement it. We use priority queues when we want to order a queue based on some type of priority value. This means that each element has a certain priority, and the priority of the elements determine the order in which elements are removed from the priority queue. The easiest way to implement a heap is actually by not using a binary tree, but rather using an array data structure. If you look at each node in this binary heap, you would see that each node has an index, which is representing its index in the array. So if we transition to the array view, this is how our binary heap looks like. The root element, which is 92, is positioned at index 1, and we don't use the index 0 in this case. The node on the left side of the root, which is 89, is positioned at index 2, and the right node of the root, which is 91, is positioned at the index of 3, and so on. So with array representation, the root node starts at index 1, and we have basic equations to determine the relationships between the nodes in our array. For example, if we want to determine the left node of the 82, we need to multiply its index by 2, which will be 20, and it's a 19 node. And indeed, you can see that the left node on 82 is 19. If we want to determine the right node of the 82, we need to multiply its index by 2 and do plus 1, which will be 21 index, and it's the 18 node. And if you look at the tree, you can see that 18 is on the right side of the 82. And one more property we will need while traversing the tree is the parent. So if we want to get the parent of this node, we need to divide the index of it by 2, which will be 5. And in case it's not a round number, we round it down. For example, if it's 9th index, we divide it by 2, it's 4.5, and we round it down to 4. So the parent of 45 should be 67. And we can verify that from the tree representation of this heap. And this representation takes advantage of the properties of a complete binary tree and allows for easy navigation between parent and child nodes without needing pointer and reference-based tree node structures. The primary operations on heaps are inserting an element, extracting the maximum minimum element, and heapifying to maintain the heap property. Let's start from insertion. Insertion is also sometimes called push on heaps. For example, if we want to push 92 node on our tree, to push 92 we first add it to the next available position and then we compare it with its parent. If the parent is smaller than 92, we swap it. Otherwise, if we reach the position where the parent is no longer smaller than 92, we leave it at that position. We use the Heapify up helper method, which is doing the necessary comparisons and swapping if it's necessary. And the time complexity of inserting an element is O of log n. Now let's see how we can extract or remove a node from our tree. If we want to just look at the top item of our heap, it's a O of 1 operation. We just have to look at the first index in our array. But if we want to remove the max element, which is the root 92 in this example, when we remove the top element in our tree, we should replace it to maintain the structure and not introduce a hole. So we replace it with the last element from the array. And then we take the top element in our tree and start to heapify it down until the heap property is satisfied. And the time complexity of removing the top element is similar to insertion. It is O of log n. One more common operation on heaps is Heapify, which is used to convert a list or array into a heap. We first add the array to our heap and then we start looping through every element, and for each item we heapify it down to maintain the heap property. And at the end of heapify function we will have a complete binary heap. And the time complexity of building a heap is O of n, which might be surprising at first because the heapify down operation itself has a time complexity of log n. However, the overall process of building a heap from an unsorting array is more efficient due to the structure of the heap and the properties of heapify down operation. Therefore, the overall time complexity for heapify function is O of n. Thanks for watching and subscribe for more tutorials like this.